Right now, as you read this, something invisible is passing through your body. Billions of particles are streaming through every cell, through the walls around you, through the entire Earth. You cannot see them. You cannot feel them. Yet they carry secrets about the universe's birth, about the nature of reality itself. Science can detect them, count them, even predict their behavior with stunning accuracy. But here's what will keep you awake tonight. We have absolutely no idea what they are. This invisible tide is dark matter, and it makes up 85% of all matter in existence. Everything you've ever seen, every star photographed, every atom mapped, every mountain climbed, every ocean crossed, all of it, all the matter we understand, is barely 15% of what's actually out there. We live in a universe where we're the minority, where the visible is the exception, where the stuff we call reality is just a thin, glittering foam on an ocean of mystery we cannot fathom. And that's just the beginning. What if I told you that dark matter isn't even the strangest part? That there's something even more pervasive, even more mysterious, pushing the very fabric of space apart at an accelerating rate. That 68% of the universe's total mass energy is composed of something we've named dark energy, despite having virtually no idea what it is, how it works, or why it exists. Do the math with me. Dark matter, 27%. Dark energy, 68%. Everything we understand, the atoms, the elements, the physics in our textbooks, adds up to barely 5% of existence. We are not just in the dark. We are an island of light in an ocean of darkness. And we're only now beginning to realize how small our island truly is. Tonight, we descend into that ocean. 100 mysteries that science, despite all its brilliance, cannot yet solve. Some will surprise you. Others will unsettle you. A few might fundamentally change how you see reality, because the greatest scientific discoveries aren't always answers. Sometimes they're questions we never knew we should ask. Prepare yourself. You're about to learn just how little we actually know. Some of these mysteries may be solved in your lifetime. Others may endure for centuries. A few might be fundamentally unsolvable, locked behind barriers we cannot yet imagine. But each one tells us something profound. That wonder is not the opposite of knowledge, but its companion. That uncertainty is not a flaw in our understanding, but a feature of reality itself. So let your thoughts settle. Let your breathing slow. And prepare to drift through the most beautiful admission science can make. We do not know everything, and perhaps we never will. Hello there, and welcome to Sleepable Science. I'm so glad you found your way here. Tonight's journey might disturb you. Not with horror or fear, but with wonder so profound it borders on vertigo. We're about to explore the boundaries of human knowledge, and what we'll find there isn't reassuring certainty, but beautiful, terrifying mystery. Before we begin, I want to share something that changes everything. In 2024, scientists studying the oldest light in the universe, the cosmic microwave background, found something that shouldn't be there. Patterns, structures, features that our best cosmological models cannot explain. They call it anomalies in the Standard Model. But what if it's evidence that our entire understanding of the universe's history is incomplete? That the Big Bang story we've told for decades is missing crucial chapters? Hold that thought. We'll return to it. Because that's just one of 100 threads we're about to pull tonight. The Japanese concept of mo I toma mo sa mo a tsokin so speaks of the spaces between things, the pause between notes that gives music its meaning, the emptiness that defines a room, the silence that makes speech possible. Tonight, we explore a different kind of ma, the space between knowing and not knowing, the fertile void where science reaches its limits and mystery begins. These mysteries are not failures. they are invitations. Each unsolved question is a doorway, a threshold, a place where reality whispers secrets we haven't yet learned to hear. Some are ancient riddles that have puzzled humanity since we first looked up at the stars. Others are fresh puzzles, born from our newest technologies and deepest probings into the nature of things. Together, they form a map not of what we know, but of what remains gloriously, beautifully unknown. You'll hear about particles that seem to know they're being watched, about time that might not flow in the direction we think, about consciousness that may extend beyond the brain, about life that began in ways we cannot yet explain, about forces we can measure but cannot see, energies we can feel but cannot touch, and questions that grow deeper the more closely we examine them. There is a kind of peace in not knowing, a quiet humility in standing before the vast mystery of existence and simply observing without needing to explain. The physicist Niels Bohr once said that anyone who is not shocked by quantum theory has not understood it. Tonight, you may be shocked. You may be confused. You may feel the ground of certainty shift beneath your understanding. That is not a bug. It is a feature. It is the honest response to reality's true nature. If these gentle explorations spark your curiosity, if they help you drift into sleep with a sense of wonder, or if they simply give you permission to not know, consider liking and subscribing to the channel. It helps others find their way here too, one curious mind at a time. But for now, settle in, take a deep breath, and let's begin our slow descent into the mysteries that science, for all its brilliance, still cannot explain. The cosmos and its shadows. Dark matter's hidden dance. Across the universe, galaxies spin too fast. According to everything we know about gravity and motion, they should tear themselves apart. Stars at the outer edges of spiral galaxies orbit at speeds that defy Newton's laws and Einstein's equations. The math is simple. There isn't enough visible mass to hold them together. Yet they hold, bound by something we cannot see. We call this invisible scaffolding dark matter. And based on gravitational measurements and galaxy rotation curves, it appears to comprise roughly 27% of the universe's total mass energy content, as reported by NASA and other space agencies. We can infer its presence the way you know wind exists by watching leaves move. Galaxies cluster in patterns that only make sense if vast halos of invisible matter surround them. Light from distant objects bends around concentrations we cannot detect directly, an effect called gravitational lensing that provides some of our strongest evidence for dark matter's existence. But what is it actually made of? Here's where decades of searching have only deepened the mystery. The leading candidates are WIMPs, weakly interacting massive particles, theoretical objects that would rarely interact with normal matter. Underground detectors have been waiting in darkness for years, hoping to catch a single collision. The LUX Zeppelin experiment, buried 1,500 meters beneath South Dakota, has found nothing. No WIMPs. Not yet. Then there are actions. Ghostly particles proposed to solve other physics problems that might also be dark matter. Or perhaps primordial black holes, formed in the universe's first fractions of a second. Each theory predicts different properties, different detection methods, different implications for reality's structure. But here's what keeps physicists awake. What if our theories of gravity are simply wrong? What if dark matter isn't matter at all, but a sign that we fundamentally misunderstand how mass and space interact on galactic scales? Some researchers propose modified Newtonian dynamics, or MOND, which suggests gravity behaves differently at vast distances than Einstein predicted. The evidence doesn't currently support MOND over dark matter, but the possibility haunts the field. We might be building elaborate theories about invisible particles, when the real answer is that gravity itself is stranger than we thought. Either way, invisible matter or modified laws, the universe is not what our textbooks claim. And here's the twist that changes everything. In 2023, astronomers discovered entire galaxies that seem to contain almost no dark matter at all. How can that be? If dark matter is fundamental to galaxy formation, how do these anomalous galaxies exist? The answer might reveal whether dark matter is a particle, a force, or something we haven't imagined yet. The accelerating universe. In 1998, astronomers made a discovery that defied expectation. The universe is not just expanding, it's accelerating. Distant supernovae appear fainter than they should be, pushed farther away by some repulsive force threading through the fabric of space itself. We name this force dark energy, and it comprises roughly 68% of the universe's total mass energy content. But naming is not understanding. Dark energy seems to be a property of empty space itself, a cosmological constant that Einstein once called his greatest blunder. Yet here it is, confirmed by multiple independent observations, pushing galaxies apart faster and faster. Is it truly constant, or does it change over time? Some theories propose quintessence, a dynamic field that evolves as the universe ages. Others suggest we're witnessing the first signs that general relativity breaks down at cosmic scales. And there's an even stranger possibility, that dark energy and dark matter are connected, two faces of a single phenomenon we barely glimpse. According to physicist Saul Perlmutter, who shared the Nobel Prize for discovering cosmic acceleration, we are living in a time when the universe's fate hangs in mystery. Will expansion continue forever, leaving galaxies isolated in darkness? Will some future shift reverse the process? Or is there a fate we haven't imagined, waiting billions of years ahead? The universe rushes apart, carried by energy we cannot explain, toward a destiny we cannot predict. The Hubble tension, when numbers don't add up. Measuring the universe should give consistent results. Scientists use the term cosmological parameters, fundamental numbers that describe the universe's structure and evolution. These should be the same no matter how we measure them, but they're not. When astronomers measure the rate of cosmic expansion, the Hubble constant, using observations of the early universe's remnant light from the cosmic microwave background, they consistently get one number, about 67 kilometers per second per megaparsec. When they measure it using nearby supernovae and other stellar distance markers, they get a different number, about 73 kilometers per second per megaparsec. The discrepancy is roughly 10%, which might not sound dramatic, but in cosmology, this is a crisis. It's as if two different methods for measuring the speed of light gave you answers that differ by thousands of miles per second. The measurements are so precise that the difference can't be explained by experimental error. Something is fundamentally wrong. This is the Hubble tension, and it may be telling us something profound about reality itself. Here are the possibilities, and none of them are comforting. Either our measurements contain systematic errors we haven't found, which seems increasingly unlikely as more independent observations confirm the discrepancy, or our understanding of cosmic evolution is fundamentally incomplete. Perhaps dark energy hasn't been constant throughout cosmic history. Perhaps it changed its strength over time, accelerating expansion faster in some epochs than in others. Or perhaps, and this is where it gets truly strange, the cosmological principle itself is wrong. This principle, which underpins all of modern cosmology, assumes the universe looks roughly the same in all directions when viewed on large enough scales. But what if that's not true? Some researchers have proposed we might live in a vast cosmic void, a region of below average density where local expansion differs from the universal average. Imagine the universe as a sponge, with dense walls and empty pockets. If we happen to inhabit one of the empty pockets, the expansion rate we measure locally could differ from the average cosmic expansion. This would mean our view of the universe is fundamentally skewed by our location. We're not seeing the whole picture because we're sitting in an unusual place. The implications are staggering. If the cosmological principle is wrong, then everything we think we know about the universe's size, age, and fate might need revision. The Big Bang might look very different than we've imagined. The distribution of dark matter and dark energy might vary by location, and there might be regions of the cosmos so different from our own that our physics simply doesn't apply there. Nobel laureate Adam Rees, who shared the prize for discovering cosmic acceleration, has spent years refining these measurements. In a 2024 interview, he stated that the tension has only sharpened with each new dataset. "We've checked every possible source of error we can think of," he noted. "The tension persists. This is either the most stubborn, systematic error in history, or we're missing something fundamental about how the universe works." Here's the twist that connects to everything. Remember those anomalies in the cosmic microwave background? Some researchers have proposed they might be connected to the Hubble tension. If our universe collided with another during the Big Bang, it could have created both the strange patterns we see in ancient light and the expansion rate discrepancy we measure today. The same event might explain both mysteries. Or perhaps early dark energy, active only in the universe's first moments, altered cosmic history in ways our models don't capture. Or perhaps our understanding of how light travels across cosmic distances contains errors we haven't recognized. Whatever the answer, one thing is certain: something in our cosmic story is wrong. And until we figure out what, every conclusion we draw about the universe's past and future rests on shaky ground. The horizon problem. In the beginning, according to our best models, the universe emerged from an infinitesimally small point in an event we call the Big Bang. Within fractions of a second, space expanded and cooled, eventually forming the atoms and light we see today. When we look at the cosmic microwave background, the universe's baby picture, we see something remarkable. It's almost perfectly uniform in temperature, varying by only 1 part in 100,000. But here's the problem. Regions on opposite sides of the observable universe have never been in contact. Light hasn't had time to travel between them. So, how did they end up at the same temperature? How did distant parts of space coordinate to create such uniformity? The leading explanation is cosmic inflation, a period of exponentially rapid expansion in the universe's first instant that stretched space faster than light could travel, smoothing out irregularities before they could form. It's an elegant solution, but it raises new questions. What caused inflation? What is the inflaton field that drove it? Why did it stop? Alternative theories propose varying speed of light in the early universe, or suggest that the Big Bang wasn't the beginning at all, but a transition from a previous state. Each solution creates new mysteries, and the horizon problem remains a window into physics we don't yet understand. Why is there something rather than nothing? Perhaps the deepest question we can ask: why does the universe exist? Why is there matter, energy, space, and time, rather than absolute nothingness? This isn't just philosophy, it's physics. The laws of quantum mechanics tell us that empty space isn't truly empty, but seethes with virtual particles, brief fluctuations of energy that appear and vanish in instants. Some theories propose that the universe itself is such a fluctuation, a quantum event that happened to persist and expand. But this only pushes the question back. Why do the laws of physics exist? Why these laws and not others? The fundamental constants of nature, the strength of gravity, the mass of electrons, the speed of light, appear finely tuned to allow complexity and life to emerge. Change any of them slightly, and stars wouldn't form, atoms wouldn't bond, and existence as we know it would be impossible. Physicist Victor Stenger suggested that as the early universe cooled, it transitioned to a more stable state, the way water freezes into ice. Perhaps nothingness is unstable, and something is the lower energy configuration. Others invoke the multiverse, an infinite ensemble of universes with different properties, ours being one where the constants happen to permit observers to ask such questions. As reported in BBC Science Focus magazine in 2021, physicists continue to grapple with creation itself. But the fundamental mystery endures. Why this? Why now? Why anything at all? The matter-antimatter asymmetry. According to the standard model of particle physics, the Big Bang should have created equal amounts of matter and antimatter. When these meet, they annihilate in pure energy, so the universe should have destroyed itself in its first moments, leaving only light. But here we are, made of matter, surrounded by matter. Antimatter exists only briefly in high-energy collisions and cosmic ray interactions. Something tipped the balance, creating a tiny excess of matter over antimatter, roughly one extra matter particle for every billion matter-antimatter pairs. This asymmetry allowed the universe to survive. But what caused it? The answer lies hidden in processes we cannot fully observe. CP violation, a phenomenon where certain particle interactions violate the symmetry between matter and antimatter, has been observed in weak force decays, but not in sufficient magnitude to explain the cosmic imbalance. Perhaps additional sources of CP violation exist in physics beyond the standard model. Perhaps the laws of physics themselves changed as the universe cooled, creating temporary conditions where matter production dominated. Or perhaps antimatter isn't missing at all, but segregated into distant regions of space we haven't observed. Every atom in your body, every star in the sky, exists because of this unexplained asymmetry. We are the descendants of an imbalance we don't understand. Black hole information paradox. When something falls into a black hole, what happens to the information it contained? This isn't about data in the colloquial sense, but about the fundamental quantum information describing the particle's state, its position, momentum, spin, and all other properties. According to quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must persist. But according to Stephen Hawking's calculations, black holes evaporate through a process called Hawking radiation, eventually disappearing completely. If the radiation is purely thermal, containing no information about what fell in, then the information is lost, violating quantum mechanics. This paradox has troubled physicists for 5 decades. Some propose that information is encoded in subtle correlations in the radiation. Others suggest it's stored at the event horizon, the black hole's surface, in a 2-dimensional holographic form. String theory offers scenarios where information escapes through microscopic corrections to Hawking's original calculations. But we have no way to test these ideas. Black hole evaporation takes longer than the current age of the universe for any black hole we can observe. The paradox remains theoretical, a clash between quantum mechanics and general relativity with no experimental resolution in sight. As reported by researchers studying gauge gravity duality, the question cuts to the heart of how information and reality relate. What we consider lost may merely be hidden in ways we haven't learned to perceive. The arrow of time. Time flows forward. Eggs break but don't unbreak. Milk mixes into coffee but doesn't spontaneously separate. Entropy, the measure of disorder, always increases. This is the arrow of time, enshrined in the second law of thermodynamics. But here's the mystery. The fundamental laws of physics are time symmetric. They work just as well forward or backward. If you filmed particles interacting and played the video in reverse, nothing would violate the laws of motion or electromagnetism or even quantum mechanics. So why does time have a direction? The answer lies somehow in entropy, and the fact that the early universe had remarkably low entropy, highly ordered and uniform. As the universe evolves, entropy increases, and this increase gives time its arrow. But why did the universe start with low entropy? This question connects to the Big Bang itself, and we have no definitive answer. Some physicists propose that time's arrow is an illusion, an artifact of how conscious beings experience a quantum multiverse. Others suggest multiple arrows of time exist, with different regions of the cosmos flowing in different temporal directions. And there's the possibility that entropy's arrow is connected to CP violation and the matter-antimatter asymmetry. Time itself, something we experience so intimately, remains one of physics' deepest mysteries. The cosmic censorship hypothesis. Inside black holes, the equations of general relativity predict singularities, points of infinite density where the laws of physics break down. But these singularities are hidden behind event horizons, boundaries from which not even light escapes. Roger Penrose proposed the cosmic censorship hypothesis. Nature abhors a naked singularity. But can naked singularities form? Could some gravitational collapse create a singularity visible from outside? Computer simulations suggest it's possible under extreme conditions. But we've never observed one, and the mathematics remains inconclusive. If naked singularities exist, they would be regions where physics itself fails, visible to the universe. They would challenge our deepest theories about the nature of space, time, and causality. The cosmic censorship hypothesis protects us from this, but we don't know if nature truly enforces such protection, or if we simply haven't looked hard enough. The Fermi paradox. The universe is vast and old. Our galaxy alone contains hundreds of billions of stars, many with planets in habitable zones. By statistical reasoning, intelligent life should be common. So where is everyone? This is the Fermi paradox, named for physicist Enrico Fermi, who famously asked, "Where are they?" Given the age of the universe and the apparent ease with which life arose on Earth, we should see evidence of advanced civilizations everywhere. Megastructures, terraformed worlds, radio signals, self-replicating probes. Yet we see nothing. The great silence pervades the cosmos. Explanations abound. Perhaps life is rare, and we are alone. Perhaps intelligence is common, but spacefaring civilization is not. Perhaps advanced species destroy themselves before spreading. Or perhaps they exist but remain hidden, either deliberately or because their technology is so advanced we cannot recognize it. Some propose the dark forest hypothesis. The universe is full of predatory civilizations that remain silent to avoid detection. Others suggest that intelligence inevitably transcends physical form, leaving the material universe behind. And there's the possibility that we're simply too early, the first in our corner of the cosmos to develop technology. Each explanation carries profound implications for humanity's future and our place in the universe. Fine-tuning of physical constants. The universe's fundamental constants appear exquisitely tuned for life. If gravity were slightly stronger, stars would burn out before life could evolve. If the electromagnetic force were slightly different, atoms wouldn't form. If dark energy were much larger, galaxies would never have formed. This fine-tuning suggests either remarkable coincidence or deeper explanation. The anthropic principle states that we observe these values because we couldn't exist otherwise. In a universe with different constants, there would be no one to wonder about it. The multiverse offers an explanation. If infinitely many universes exist with different constants, Ours is simply one where conditions permit observers. But this raises the question of what mechanism generates such universes, and whether the multiverse hypothesis is even testable. Others suggest the constants aren't truly constant, but evolved to current values through processes we don't understand. Or perhaps our theories are incomplete, and what appears as fine-tuning is actually a consequence of deeper laws that require these specific values. Physicist Steven Weinberg has noted that the cosmological constant, in particular, appears tuned to within one part in 10^120, an almost inconceivable precision. Whether this reflects design, chance, or physics beyond our understanding remains one of the most profound open questions. The shape and size of the universe. We know the observable universe is roughly 93 billion light-years in diameter, expanded from its origin 13.8 billion years ago. But what lies beyond what we can see? Is the universe infinite? If so, how can something that began as a singularity become infinite? If it's finite, what defines its boundary, and what lies beyond? These questions probe the nature of space itself. The universe's shape is equally mysterious. Is it flat, curved like a sphere, or hyperbolic like a saddle? Current measurements suggest it's remarkably close to flat, but we cannot rule out subtle curvature. The topology, how space connects to itself, remains unknown. The universe could be a three-dimensional equivalent of a torus, where traveling far enough in one direction brings you back to where you started. And there's the possibility of other bubble universes, floating in higher dimensional space, each with its own physical laws. We cannot see beyond our cosmic horizon, the limit set by the finite speed of light and the universe's age. What lies beyond may be forever unknowable. The quantum world and its strangeness. The measurement problem. Quantum mechanics describes particles as existing in superposition, multiple states simultaneously, until measured. A photon can be spinning both clockwise and counterclockwise. An electron can be in many places at once. But when we measure, the superposition collapses into a single, definite state. What causes this collapse? The equations of quantum mechanics describe superposition beautifully, but say nothing about measurement. When does collapse occur? What counts as measurement? These questions have plagued physics for nearly a century. The Copenhagen interpretation, the oldest solution, simply asserts that measurement causes collapse without explaining the mechanism. The many worlds interpretation proposes that collapse never happens. Instead, the universe splits into branches where each possible outcome occurs. Decoherence theories suggest that interaction with the environment causes apparent collapse. But we still don't know. As physicist John Bell noted, quantum mechanics works spectacularly well for prediction, but tells us nothing about what is actually happening. The measurement problem remains the central puzzle of quantum theory. Wave-particle duality. Light behaves as waves, creating interference patterns when passed through slits. But it also behaves as particles, photons that can be counted and detected individually. Electrons, atoms, even molecules show the same dual nature, acting as waves in some experiments and particles in others. How can something be both? The question becomes even stranger when you run the double-slit experiment one photon at a time. Each photon passes through the apparatus alone, yet the pattern that builds up over many individual photons shows wave interference, as if each photon somehow went through both slits simultaneously. And if you set up detectors to determine which slit each photon passes through, the interference pattern disappears. The act of measurement changes the outcome. This isn't a technical limitation, but something fundamental about reality itself. Physicist Richard Feynman called this the only mystery of quantum mechanics, the phenomenon that contains all the strangeness of the quantum world. Decades later, we can describe it mathematically, predict its outcomes precisely, but we still cannot explain how or why nature behaves this way. Quantum entanglement. When two particles interact in certain ways, they become entangled. Afterward, measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, and argued it proved quantum mechanics incomplete. But experiments have confirmed it repeatedly. Measure the spin of one entangled electron, and its partner's spin instantly becomes determined, even if they're separated by thousands of miles. The correlation is perfect and instantaneous, apparently violating the principle that nothing travels faster than light. Quantum mechanics allows this without allowing faster than light communication, a subtle distinction that preserves relativity while defying intuition. But how does it work? What connects entangled particles across space? Some interpretations suggest a holistic view where entangled particles remain a single system, regardless of separation. Others propose hidden connections in higher dimensions or through structures we cannot perceive. The phenomenon is real, verified, and foundational to quantum computing, yet its mechanism remains mysterious. The quantum to classical transition. Quantum mechanics governs the atomic world beautifully. Classical physics describes everyday objects with equal precision. But where and how does one transition to the other? Cats are both alive and dead in quantum superposition, according to Schrödinger's famous thought experiment. But we never observe macroscopic superpositions. Somewhere between atoms and cats, quantum behavior gives way to classical certainty. Where is that boundary? Decoherence, the interaction with environment that destroys quantum coherence, offers a partial answer. But it doesn't truly explain why measurement yields single outcomes, or how quantum probabilities become classical certainties. The transition from quantum to classical involves a fundamental change in how reality behaves, and we don't fully understand it. Recent experiments have demonstrated quantum effects in larger and larger systems, molecules with thousands of atoms showing interference. But a true macroscopic quantum superposition remains elusive, and the boundary between worlds undefined. Quantum contextuality. In classical physics, properties exist independently of how we measure them. A ball has a color whether or not anyone looks at it. But quantum mechanics suggests that properties don't exist until measured, and which properties we can know depends on what we choose to measure. This is contextuality. Measuring an electron's position with high precision makes its momentum fundamentally uncertain, not just unknown, but undefined. The properties depend on the context of measurement, like words whose meaning shifts with context in language. As physicist Adon Cabello has noted, contextuality is as strange as non-locality, but receives less attention. It challenges our assumption that objects have well-defined properties existing independently of observation. Recent experiments have confirmed contextuality in systems where non-locality plays no role, proving it's a distinct feature of quantum reality. This suggests that reality, at its deepest level, is relational rather than absolute, defined by measurements and interactions rather than existing independently. What we take as solid facts may be contextual truths, dependent on how we engage with the world. The quantum vacuum. Empty space is not empty. According to quantum field theory, even vacuum seethes with virtual particles, brief fluctuations of energy that appear and disappear in time intervals so short that the uncertainty principle permits them. These virtual particles are not mathematical abstractions. They have measurable effects. The Casimir force between parallel plates, the slight shift in atomic energy levels, and even the polarization of light passing through magnetic fields. The vacuum has structure and energy. But how much energy? When physicists calculate the vacuum's energy density from quantum field theory, they get a number that is 10 to the 120 times larger than the cosmological constant we observe. This is the cosmological constant problem, perhaps the worst prediction in the history of physics. Something must cancel out most of the vacuum energy, but we don't know what. The mechanism that makes the vacuum's energy nearly, but not quite, zero remains one of physics' deepest mysteries. Quantum tunneling. In the quantum world, particles can pass through barriers that classical physics says should be impenetrable. An electron can tunnel through a barrier without having enough energy to climb over it. It simply appears on the other side. This isn't magic or approximation. It's how radioactive decay works, how scanning tunneling microscopes image atoms, and how the sun fuses hydrogen into helium. Tunneling is real and essential. But how does it happen? How does a particle traverse a barrier without passing through the space between? Quantum mechanics provides probability amplitudes that predict tunneling rates precisely, but offers no picture of the journey itself. Some interpretations suggest the particle exists in superposition on both sides of the barrier simultaneously until measurement. Others propose that asking about the particle's path is meaningless. Either way, tunneling reveals something fundamental about how reality operates at the quantum level that we still struggle to comprehend. The role of the observer. Does consciousness play a role in quantum mechanics? The measurement problem suggests that observation collapses wave functions. But what constitutes an observer? Must it be conscious? Can a machine make measurements, or does awareness matter? Some physicists, including Eugene Wigner, proposed that consciousness is necessary to collapse wave functions, making minds fundamental to physical reality. Others argue that any interaction with a macroscopic system constitutes measurement. Consciousness is irrelevant. Recent experiments suggest that quantum systems can observe each other without consciousness involved. But the question persists: what is special about measurement? Why does observation create definite outcomes from quantum superposition? The relationship between mind and matter, between observation and reality, remains unresolved. Whether consciousness is a quantum phenomenon or emerges from classical neural processes is an active area of research, with profound implications for how we understand both physics and ourselves. Quantum randomness. When you measure a quantum system in superposition, the outcome is random. Not pseudo-random, like a computer's number generator, but truly random. This randomness appears fundamental to nature. Einstein famously objected, declaring, "God does not play dice." He believed hidden variables must determine the outcomes. That apparent randomness masks deeper determinism. But experiments testing Bell's inequalities have ruled out most hidden variable theories. The randomness seems truly irreducible. But why? What makes one outcome occur rather than another? Quantum mechanics provides probabilities, but it cannot, even in principle, predict individual results. Some interpret this as evidence that determinism is false, that the universe's future is not determined by its present state. Others suggest randomness only appears in our universe, while determinism holds in a larger multiverse. The question touches the nature of causation and reality itself. Quantum gravity. Gravity operates by warping spacetime, according to general relativity. Quantum mechanics describes forces through particle exchange. But attempts to quantize gravity, to describe it in quantum terms, have failed for decades. At the Planck scale, roughly 10⁻⁵ meters, quantum effects and gravitational effects become equally important. At these scales, space and time themselves should become quantum, subject to uncertainty and superposition. What does that mean? We don't know. String theory offers one approach, replacing particles with vibrating strings in 10 dimensions. Loop quantum gravity proposes that space is fundamentally discrete, made of tiny quanta. Both face mathematical and experimental challenges. The problem isn't just technical. Quantum mechanics and general relativity make fundamentally different assumptions about the nature of space, time, and causation. Unifying them may require rethinking our deepest concepts about reality, consciousness, and the mind. The hard problem of consciousness. How does subjective experience arise from physical processes? Why is there something it's like to be you, to see red, to feel pain, to experience joy? This is what philosopher David Chalmers termed the hard problem of consciousness, and it's remained unsolved for centuries. We can study neural correlates, identifying brain regions active during specific experiences. We can map how information flows through neural networks. We can even predict which brain states correspond to which conscious experiences. But these are what Chalmers calls the easy problems. The hard problem is explaining why any physical process should give rise to inner experience at all. Here's what makes this truly unsettling. Neuroscientist Christoph Koch has pointed out that we don't even understand consciousness in simple organisms. The roundworm C. elegans has just 302 neurons that have been completely mapped, every single connection charted. Yet we still cannot fully explain its behavior, or determine whether it has any form of subjective experience. Humans have roughly 86 billion neurons and an estimated 100 trillion connections. If we can't explain awareness in 302 neurons, how can we hope to understand it in billions? But here's where it gets strange. Recent research suggests consciousness might not emerge from complexity at all. Some of the most sophisticated neural networks we've built, with complexity rivaling simple animal brains, show zero signs of subjective experience. Meanwhile, patients in vegetative states, with severely damaged brains showing minimal activity, sometimes retain hidden awareness that only advanced imaging can detect. This pattern hints that consciousness might not be what we think it is. If it's not simply an emergent property of complex neural networks, then what is it? The integrated information theory, proposed by neuroscientist Giulio Tononi, suggests something radical. Consciousness might be a fundamental feature of reality, present wherever information is integrated above a certain threshold. This theory, if true, would mean that some degree of subjective experience could exist in systems we'd never expect, possibly even in artificial systems, if structured correctly. Others propose that quantum effects in microtubules within neurons might be essential, linking consciousness to the quantum realm's strange properties. Physicist Roger Penrose and anesthesiologist Stuart Hameroff developed this theory, though it remains controversial and unproven. The question touches everything from artificial intelligence to the nature of death. If consciousness emerges from complexity, then sufficiently advanced machines might become truly aware, not just mimicking awareness, but actually experiencing it. If it's fundamental to reality, then it might exist in forms we've never considered and possibly persist beyond brain death in ways we don't yet understand. We simply don't know, and that uncertainty means we don't know what we are. The binding problem. Your experience feels unified. When you see a red ball rolling across the floor, the redness, roundness, and motion combine into a single, coherent perception. But these features are processed in different brain regions, separated by centimeters and milliseconds. How does the brain bind these separate processes into unified experience? This is the binding problem, and despite decades of research, we have no definitive answer. Some propose that synchronized neural oscillations, particularly gamma waves around 40 kHz, bind features together. When neurons fire in sync, their outputs combine into coherent representations. But experiments testing this have yielded mixed results. Others suggest that attention acts as the binding agent, selecting and integrating relevant information. Or perhaps binding is an illusion, and what we experience as unity is actually a constructed narrative our brains create after the fact. The problem extends beyond perception to consciousness itself. How do billions of separate neural events combine to create a single stream of awareness? What makes you a unified self rather than a collection of independent processes? The neural correlates of consciousness. Which brain processes give rise to conscious experience? Decades of neuroimaging and lesion studies have identified regions associated with consciousness: the thalamus, cortex, claustrum, and specific networks linking them. But association is not explanation. We can identify where and when neural activity correlates with conscious states, but we cannot explain why these particular patterns create awareness while others don't. The global workspace theory proposes that consciousness arises when information becomes globally available across the brain, broadcast to multiple systems. Integrated information theory suggests consciousness corresponds to integrated information, a mathematical measure of how much a system is more than the sum of its parts. As described in research published in Neuroscience of Consciousness in 2024, recent studies using transcranial magnetic stimulation to test these theories have yielded surprising results. Stimulating brain regions thought critical for consciousness sometimes fails to affect perception, suggesting our models remain incomplete. We can correlate brain states with conscious experiences, but we still cannot explain why correlation exists or how neural firing becomes subjective feeling. Free will and determinism. Do we have free will, or are our choices determined by prior causes? Neuroscience has made this ancient philosophical question empirical. Brain activity corresponding to decisions can be detected seconds before people report conscious awareness of choosing. These findings suggest that what we experience as free will might be an illusion, a narrative our brains construct after unconscious processes have already decided. But the interpretation is contested. Some argue that unconscious brain activity is still us making decisions, just not the conscious aspect we identify with. Others propose that quantum indeterminacy in neural processes could permit genuine freedom. And there's the question of what freedom means in a deterministic universe where randomness exists. The relationship between consciousness, causation, and choice remains mysterious. We know brain activity precedes conscious intention, but we don't know if this eliminates free will or simply reveals its neural implementation. The function of sleep and dreams. We spend roughly a third of our lives asleep, cycling through distinct stages with different brain activity patterns. Why? Sleep clearly serves multiple functions: memory consolidation, metabolic regulation, cellular repair. But we don't fully understand the mechanisms or why consciousness must shut down for these processes to occur. Dreams are even more mysterious. During REM sleep, the brain becomes nearly as active as during waking, yet we experience bizarre narratives disconnected from external reality. What purpose does dreaming serve? Theories range from memory processing and emotional regulation to random neural firing with no function. Some propose dreams simulate threats, preparing us for challenges. Others suggest they reveal unconscious processes or integrate daily experiences with long-term memory. As noted in PMC's research on consciousness mysteries, the default space model and other theories attempt to explain these phenomena, but sleep and dreams remain incompletely understood. What happens to consciousness during dreamless sleep? Does awareness persist in altered form or truly cease? The nature of memory. How are memories stored? We know synapses strengthen and weaken, that neural connections change with experience. But where exactly is a memory? Attempts to find memory traces, engrams, in specific neurons have yielded partial success. researchers can identify neurons active during memory formation and later recall. But memory seems to be distributed rather than localized, resistant to precise anatomical mapping. Long-term memory involves protein synthesis and structural changes at synapses. But the chemical details of how transient neural activity becomes permanent memory remain elusive. As neuroscientist Eric Kandel has stated, memory recall is a deep problem whose analysis is just beginning. False memories demonstrate that recollection is reconstruction, not playback. We don't retrieve stored files, but rebuild experiences from fragments, a process prone to error and influence. What we remember may differ significantly from what occurred. And there's the question of why we remember some things, but not others. What determines which experiences become permanent memory, and which vanish? Subjective time perception. Time feels different in different contexts. Childhood summers stretched endlessly. Emergency moments slow to a crawl. Hours vanish in engaging activities. Why does time's passage feel variable? Neuroscience has identified brain regions involved in timing, particularly the basal ganglia and cerebellum. But understanding neural clocks doesn't explain why their ticking feels fast or slow. Attention may play a role. When we're engaged, time flies because we're not monitoring its passage. In boredom or fear, heightened attention to time's flow makes it feel slower. Memory density also matters. Periods we remember as rich in events feel longer in retrospect than empty spans. But these explanations remain incomplete. The relationship between physical time, neural processes, and subjective experience remains poorly understood. Why does consciousness experience time at all? Why not simply exist in an eternal present? The unity of self. You feel like a single unified person, continuous from childhood to now. But split-brain patients, whose corpus callosum has been severed, suggest consciousness might not be unitary. In these patients, each hemisphere processes information independently. Asked to point to objects with different hands, they may give conflicting answers, as if two separate consciousnesses inhabit one brain. This challenges the assumption that consciousness is necessarily singular. The sense of self appears to be constructed from multiple processes: memory, perception, body awareness, narrative construction. These normally integrate seamlessly, but brain damage can dissociate them, creating bizarre conditions where people deny owning their own limbs or believe their loved ones are imposters. What unifies these processes into a coherent self? Is the self an illusion, a useful fiction the brain maintains? Or is there some integrating principle we haven't identified? The question matters for understanding identity, responsibility, and what it means to be a person. Qualia and subjective experience. What is it like to see red? Not the wavelength of light or neural firing pattern, but the subjective quality of the experience itself. These raw feels, called qualia, represent a fundamental puzzle. We can never know if your red looks like my red. We might agree that ripe tomatoes and stop signs share a color, but the internal experience might differ completely. Qualia are private, ineffable, and resistant to objective description. Philosopher Frank Jackson proposed the knowledge argument. Imagine Mary, who knows everything about color vision from studying it in black and white. When she finally sees color, does she learn something new? If yes, then there's more to consciousness than physical facts. Some argue qualia don't exist as separate from brain states. Others propose they're fundamental features of reality, perhaps related to quantum processes. Either way, the subjective quality of experience remains unexplained by current neuroscience. Altered states of consciousness. Meditation, psychedelics, near-death experiences, and other altered states reveal consciousness's malleability. Under certain conditions, the boundaries of self dissolve, time distorts, and reality appears radically different. What do these states tell us about normal consciousness? Are they aberrations, or do they reveal aspects usually hidden? Neuroscience has begun mapping the brain changes accompanying altered states, finding decreased activity in the default mode network and altered connectivity patterns. But understanding the neural correlates doesn't explain the experiences themselves. Why does decreased brain activity sometimes lead to feelings of expanded consciousness? How do different altered states relate to each other and to baseline awareness? These questions bear on consciousness's nature and potential. If awareness can radically reconfigure itself, what does that imply about its normal structure? Are we experiencing only one mode of consciousness among many possible ones? Life, evolution, and origins. The origin of life. How did life begin? How did non-living chemistry become biology? This is among science's most profound mysteries. And despite decades of research, we have hypotheses, but no definitive answer. The building blocks are surprisingly easy to create. Stanley Miller and Harold Urey demonstrated in 1952 that simple compounds like methane and ammonia exposed to energy sources spontaneously form amino acids. Meteorites contain organic molecules, suggesting the ingredients for life pervade the cosmos. But having parts doesn't explain assembly. How did amino acids become proteins? How did random molecules develop the ability to replicate, the defining feature of life? And which came first? Metabolism, the chemical processes that extract energy, or genetics, the ability to store and transmit information. The RNA world hypothesis proposes that RNA, which can both store information and catalyze reactions, preceded DNA and proteins. But this only pushes the question back. How did RNA arise? Recent research, as described in work published in the Proceedings of the National Academy of Sciences in 2023, suggests electron transport chains may have formed through mineral-driven reactions before life existed. Hydrothermal vents, underwater volcanoes, and warm little ponds have all been proposed as life's birthplace. Each environment offers different advantages and challenges. The fact that we still don't know hints at how remarkable life's origin must have been. The Cambrian explosion. For billions of years, life remained simple. Single cells, then basic multicellular organisms. Then, roughly 540 million years ago, complex animals suddenly appeared in the fossil record. In just 20 million years, most major animal groups emerged. This is the Cambrian explosion, and we still cannot fully explain it. What triggered such rapid diversification? One hypothesis suggests rising oxygen levels enabled complex body plans. Another proposes that predation drove an evolutionary arms race, selecting for defensive structures and mobility. The evolution of eyes might have accelerated change as vision opened new ecological niches. But recent research has challenged the oxygen hypothesis, with some evidence suggesting oxygen levels were declining during the Cambrian. Others propose that the explosion wasn't a singular event, but a series of evolutionary pulses. And there's the possibility that our perception of suddenness is an artifact of incomplete fossil records. What is clear is that something fundamental changed, allowing life to explore body plans and lifestyles previously impossible. The trigger for this transformation remains debated. The tree of life's root. All life descends from a common ancestor, a single organism that lived billions of years ago. But what was this ancestor? Luca. Last universal common ancestor. And how did it live? Luca probably existed around 3.5 to 4 billion years ago, but reconstructing its properties from modern organisms is challenging. Different analysis methods yield different conclusions about its metabolism, habitat, and structure. Some evidence suggests Luca lived near hydrothermal vents, using chemical energy from volcanic reactions. Others propose it was a simpler form, perhaps not even cellular in the modern sense. And there's the question of whether Luca was a single organism or a community of entities sharing genetic material. Even deeper mystery surrounds life's branching into three domains: bacteria, archaea, and eukarya. How and when did this split occur? The root of the tree of life, the point where these domains diverge, remains uncertain despite genomic analysis of thousands of species. The origin of sexual reproduction. Sex is complicated, costly, and seemingly inefficient. An asexual organism can reproduce faster, doesn't need to find mates, and passes all its genes to offspring rather than just half. So, why did sexual reproduction evolve and persist? The standard answer is that sex increases genetic diversity, allowing populations to adapt faster to changing conditions. But this benefit seems too small to outweigh sex's costs, especially in stable environments. Alternative theories abound. Perhaps sex helps purge harmful mutations by concentrating them in some offspring. Perhaps it's a defense against parasites, which struggle to adapt when host genomes shuffle each generation. Or perhaps the benefits vary depending on species and environment. The origin of sex is equally mysterious. The first sexual organisms probably exchanged genetic material without specializing into males and females. How and why did separate sexes evolve? Why are there usually just two sexes rather than more? These questions matter beyond biology. They touch on some of life's most fundamental behaviors and the evolutionary forces that shaped them. Peto's paradox. Large animals should get cancer more often than small ones. They have more cells, more cell divisions, and more opportunities for mutations to cause malignancy. But they don't. Whales, elephants, and other giants have cancer rates similar to or lower than humans and mice. This is Peto's paradox, named for Richard Peto, who identified it in 1977. The fact that cancer risk doesn't scale with body size suggests large animals have evolved superior cancer suppression mechanisms. Elephants have multiple copies of the tumor suppressor gene p53. Whales may have enhanced DNA repair systems, but we don't fully understand these mechanisms or how they evolved. The paradox matters for human medicine. Understanding how large animals suppress cancer could reveal new treatment approaches, but it also poses fundamental questions about the evolution of multicellularity and the constraints on body size. The origin of viruses. Viruses occupy a strange position between life and non-life. They carry genetic information and evolve, but they cannot reproduce without hijacking cellular machinery. Where did they come from? Three main hypotheses exist. The virus first hypothesis proposes viruses preceded cellular life, representing early self-replicating systems. The progressive hypothesis suggests viruses evolved from escaped genetic elements that gained independence. The regressive hypothesis proposes they descended from cellular organisms that became increasingly parasitic, losing functions until only replication machinery remained. Evidence supports aspects of all three, suggesting viruses may have multiple independent origins. Different virus groups might have different evolutionary histories. But without fossils, reconstructing this history is extraordinarily difficult. Viruses blur the boundary between living and non-living, raising questions about how we define life itself. Are they alive? If not, what are they? These questions have no simple answers. The purpose of sleep. All animals sleep or show sleep-like states, suggesting it serves vital functions. Yet the precise mechanisms and full purpose remain mysterious. Sleep clearly enables memory consolidation. During deep sleep, the brain replays and reorganizes daily experiences, transferring them to long-term storage. Sleep deprivation impairs learning and memory formation, but sleep also seems to flush metabolic waste from the brain, regulate immune function, and maintain neuroplasticity. The glymphatic system, discovered only recently, clears toxic proteins during sleep that accumulate during waking. Why must we lose consciousness for these processes? Could the brain not perform maintenance while we remain aware? And why do we need multiple sleep stages with distinct brain activity patterns? As researchers have noted, despite sleep's universality and obvious importance, we still don't fully understand why we must spend a third of our lives unconscious. Monarch butterfly migration. Every year, millions of monarch butterflies migrate up to 3,000 miles from Canada and the United States to small, overwintering sites in Mexico. The journey takes multiple generations. No individual makes the round trip. How do descendants return to specific locations their great-grandparents left? They navigate using the sun as a compass, correcting for the sun's movement with an internal clock. But how is the destination encoded? How do butterflies born in Canada know to fly to a mountain forest in Michoacan they've never seen? The navigational mechanism involves both genetic programming and learned behavior. But the details remain incompletely understood. What triggers migration? How precise is their navigation? Why do they travel such vast distances when suitable habitat exists closer? This migration represents one of nature's most remarkable behaviors, yet its full explanation eludes us. The function of junk DNA. The human genome contains roughly 20,000 protein-coding genes, only about 2% of our DNA. The rest was once dismissed as junk, evolutionary debris with no function. But we now know this view is wrong. Much non-coding DNA regulates when and where genes are activated, controlling development and cellular function. Some sequences are more conserved across species than protein-coding genes, suggesting they're functionally important. But we don't understand the purpose of most non-coding DNA. Does all of it serve functions we haven't discovered? Is some truly junk, the remnants of ancient viral infections and failed genes? The question matters for understanding evolution, development, and genetic disease. Recent discoveries keep expanding the functional repertoire of non-coding DNA. Each new finding suggests we've underestimated its importance. But how much is functional and how much is neutral? Baggage remains unresolved. Parthenogenesis in complex animals. Some animals reproduce without males through parthenogenesis, unfertilized eggs developing into offspring. This makes sense in simple organisms, but it also occurs in reptiles, birds, and even rarely in sharks and other complex animals. Why does it happen? In some species, it's an adaptation to environments where mates are scarce, but in others, it occurs unpredictably alongside normal sexual reproduction. The mechanisms vary. Some species produce clones of the mother. Others use different genetic shuffling methods that maintain diversity. But the evolutionary logic remains puzzling. Why retain the capacity for parthenogenesis if sex is the norm? And there's the question of how complex developmental programs, evolved for sexual reproduction, can function with only maternal genes. What triggers this alternative reproductive mode, and what determines whether it produces viable offspring? The evolution of consciousness. When did consciousness arise? Did it emerge suddenly or gradually? Is it unique to animals with complex brains? Or does it exist in simpler forms throughout life? We don't know when organisms first experienced subjective awareness. Self-recognition in mirrors, suggesting self-awareness, appears in great apes, dolphins, elephants, and magpies. But does this mean other animals lack consciousness, or simply that they express it differently? Pain responses exist even in invertebrates, but do they feel pain or merely react to damage? Where on the evolutionary tree does experience begin? Some propose consciousness emerged gradually with increasing neural complexity. Others suggest it's a fundamental property of information processing, present in varying degrees across life. The question matters ethically for how we treat animals and practically for understanding consciousness's nature. Quantum biology. Could quantum mechanics play a role in living systems? For decades, this seemed unlikely. Biological environments are too warm and wet for delicate quantum effects to persist, but mounting evidence suggests otherwise. Photosynthesis appears to use quantum coherence to transfer energy with near-perfect efficiency. Birds may navigate using quantum effects in proteins sensitive to Earth's magnetic field. Even our sense of smell might rely on quantum tunneling. These quantum biological processes operate at room temperature in complex, noisy environments. How? What protects quantum states from decoherence? Understanding these mechanisms could revolutionize technology, but it also raises profound questions about life's nature. If quantum effects are fundamental to biology, then life may be exploiting aspects of reality we're only beginning to understand. The boundary between quantum and classical worlds may be more permeable than we thought. Chemistry, materials, and the elements. Room temperature superconductors. Some materials conduct electricity without resistance when cooled to extremely low temperatures. This is superconductivity, discovered in 1911 and explained by quantum mechanics in the 1950s. But cooling systems are expensive and impractical for most applications. A room temperature superconductor would revolutionize technology. Lossless power transmission, maglev transportation, powerful computers requiring minimal cooling. Decades of research have pushed the temperature threshold higher, but materials that superconduct at room temperature under practical conditions remain elusive. Recent claims of room temperature superconductivity have been challenged and retracted, highlighting the difficulty of both achieving and verifying such materials. The theoretical limits remain unclear. Is room temperature superconductivity impossible, or do we simply need the right material structure? The question involves fundamental physics of electron interactions and materials science at the limits of our understanding. The mechanism of high-temperature superconductivity. Even conventional superconductivity at higher temperatures than predicted remains mysterious. High-temperature superconductors, discovered in 1986, work at temperatures up to 140 degrees, much warmer than older materials, but we still don't fully understand why. The standard BCS theory that explains conventional superconductivity doesn't work for these materials. They violate expectations, involving complex copper oxide structures that challenge theoretical models. Multiple competing theories exist, but no consensus has emerged. The microscopic mechanism that allows certain materials to superconduct at relatively high temperatures remains one of condensed matter physics' central mysteries. Chemical origin of life's homochirality. Amino acids and sugars exist in mirror image forms, left-handed and right-handed. But life uses almost exclusively left-handed amino acids and right-handed sugars. Why? This homochirality seems fundamental to biology. Mixed-handedness would disrupt protein folding and cellular function. But how did life choose one form over the other? The molecules are chemically identical, with equal stability and reactivity. Yet life consistently selects specific versions. Some propose that random fluctuations in early Earth created a slight imbalance that autocatalytic processes amplified. Others suggest external influences, like circularly polarized light from stars, selected one form. But we have no definitive explanation for how this fundamental asymmetry arose or why it persists. The nature of the chemical. Bond. We teach chemistry using ball and stick models where atoms connect through bonds. But what are bonds really? Quantum mechanics describes bonds as electron probability clouds, regions where electrons are likely to be found. Linus Pauling's concept of orbital overlap and Robert Mulliken's molecular orbital theory both attempt to explain bonding quantum mechanically. But these approaches remain approximations. Calculating exact bond properties from first principles remains extraordinarily difficult, except for the simplest molecules. And fundamental questions persist. Are bonds real entities or convenient fictions? How do we define where one molecule ends and another begins? The concept that underlies all of chemistry still defies complete theoretical description. Protein folding. Proteins are chains of amino acids that fold into specific three-dimensional shapes. The shape determines function. A misfolded protein can cause disease. Alzheimer's, Parkinson's, Creutzfeldt-Jakob disease all involve abnormal protein structures. The sequence of amino acids determines the final folded shape, but predicting that shape from sequence remained impossible for decades. AlphaFold 2, released in 2020, achieved remarkable success using deep learning to predict protein structures. But this is prediction, not understanding. We still don't fully understand the physical principles governing how proteins fold. Why do they fold to one specific structure rather than many possible ones? How do chaperone proteins assist folding? What determines folding speed? And the inverse problem remains difficult: designing amino acid sequences that will fold into desired shapes. The protein folding problem may be partly solved computationally, but many mysteries remain. The maximum number of elements. The periodic table currently extends to element 118 oganesson. But how far can it go? Is there a maximum atomic number beyond which elements cannot exist? Calculations suggest that around element 137, the innermost electrons would exceed the speed of light if treated non-relativistically. More accurate models accounting for the nucleus's finite size push this limit to around element 173. But other factors constrain element creation. Heavier elements are increasingly unstable, decaying in fractions of a second. Creating them requires enormous energy and precise conditions. Whether a true limit exists, or we're just technologically limited, remains unclear. And if super heavy elements exist, their chemistry might differ radically from predictions. The periodic table's patterns may break down as quantum and relativistic effects reshape electron orbitals. Water's anomalous properties. Water is strange. It expands when freezing, unlike most substances. Its solid form floats on its liquid form. It has an unusually high boiling point for its molecular weight. It's an excellent solvent and has exceptional heat capacity. These anomalies arise from hydrogen bonding, the weak attraction between water molecules. But we still don't fully understand liquid water's structure, or how hydrogen bond networks organize and reorganize. Water can exist in multiple amorphous ice forms with different densities and structures. Under extreme pressure, it may form superionic ice, where oxygen atoms lock in place, while hydrogen atoms flow freely. Each discovery reveals new complexity. The most familiar substance on Earth remains surprisingly mysterious at the molecular level. Glass transition. Glass is neither solid nor liquid, but something in between. When you cool a liquid quickly enough, it doesn't crystallize, but becomes increasingly viscous until it forms glass, a disordered solid. What happens at the glass transition? Why doesn't glass crystallize given enough time? Some ancient glass does show crystallization, but the process is far slower than theory predicts. The glass transition is a phase change, but unlike melting or boiling, it lacks a sharp transition temperature. Properties change gradually over a range. The microscopic nature of this transition remains poorly understood despite its importance for materials, science, and geology. Is glass truly a non-equilibrium state, destined to eventually crystallize? Or does it represent a distinct thermodynamic phase? These questions still generate debate. Mathematics, logic, and computation. The Riemann hypothesis. One of mathematics' most famous unsolved problems concerns the distribution of prime numbers. The Riemann hypothesis, proposed in 1859, makes a precise prediction about the zeros of the Riemann zeta function, a mathematical object intimately connected to primes. If true, it would reveal deep patterns in how primes are distributed among integers. It would prove that primes, though seemingly random, follow subtle regularities. Millions of zeros have been checked and all conform to the hypothesis, yet no proof exists. The Clay Mathematics Institute offers a $1 million prize for a solution. Thousands of mathematicians have attempted proofs. The hypothesis has implications for cryptography, quantum physics, and pure mathematics. But despite 165 years of effort, we still don't know if it's true. The primes, those fundamental building blocks of arithmetic, keep their secrets. P versus NP problem. Some problems are easy to solve and easy to verify. Others are hard to solve but easy to verify. And then there are problems whose solutions are hard even to check. The P versus NP question asks, are there problems whose solutions are easy to verify but fundamentally hard to find? Or could there be an algorithm that solves all such problems quickly? This matters practically for cryptography, optimization, and artificial intelligence. It matters philosophically for understanding the limits of computation and proof. Most computer scientists believe PNP that some problems are inherently hard, but no one has proven it. The Clay Mathematics Institute offers a $1 million prize for a solution, but this problem has resisted all attempts. Its resolution would reshape computer science and possibly reveal fundamental limits to what can be computed. The nature of mathematical truth. Do numbers exist independently of human minds? Is mathematical truth discovered or invented? These questions have no scientific answer, but they profoundly affect how we understand mathematics and its relationship to reality. Platonists argue that mathematical objects exist in an abstract realm we discover through reasoning. Formalists contend that mathematics is a game of symbol manipulation with no necessary connection to reality. Intuitionists insist that mathematical objects are mental constructions. The unreasonable effectiveness of mathematics in describing nature, as physicist Eugene Wigner noted, suggests mathematics captures something real about the universe. But why should abstract human reasoning correspond so precisely to physical law? No consensus exists. The ontological status of mathematical truth remains an open question at the boundary of mathematics and philosophy. Goldbach's conjecture. Every even integer greater than 2 can be expressed as the sum of two prime numbers. This is Goldbach's conjecture, proposed in 1742. It's been verified for all even numbers up to enormous values. Yet, no proof exists. The conjecture seems obviously true, but mathematical obviousness is not proof. Many seemingly obvious statements have been proven false. The difficulty lies in prime's irregular distribution. While patterns exist, they resist the kinds of arguments needed to prove Goldbach's claim for all even numbers, not just the ones we've checked. It remains one of the oldest unsolved problems in number theory, tantalizing in its simplicity and resistance to proof. The continuum hypothesis. Between the integers and the real numbers lies an infinite gap. The integers are countably infinite. You can list them. The real numbers are uncountably infinite. No list can contain them all. The continuum hypothesis asks, Is there an infinity between these two? An infinite set larger than the integers, but smaller than the reals? Kurt Gödel proved the continuum hypothesis cannot be disproven from standard set theory axioms. Paul Cohen proved it cannot be proven either. It's independent of our axiom system, neither true nor false within the framework we use. This raises profound questions about mathematical truth. If a statement can be neither proven nor disproven, what does it mean to ask if it's true? Does mathematics describe a pre-existing reality, or do axiom choices create different mathematical universes? The unknowability of computation. In 1936, Alan Turing proved that some questions about computation cannot be answered. The halting problem asks, given a program and an input, will it eventually stop or run forever? Turing showed no general algorithm can solve this for all programs. There are computational questions that are provably unsolvable. This reveals fundamental limits to what can be computed or proven. Some mathematical statements may be true, but unprovable. Some problems may have answers we can never find. Gödel's incompleteness theorems extend this, showing that any consistent mathematical system complex enough to describe arithmetic contains true statements that cannot be proven within that system. These results suggest that complete knowledge may be impossible even in the abstract realm of mathematics and computation. The twin prime conjecture. Prime numbers often appear in pairs: 3 and 5, 11 and 13, 17 and 19. These are twin primes differing by 2. The twin prime conjecture states that infinitely many such pairs exist. It seems true. We've found vast numbers of twin prime pairs, including some with millions of digits, but no proof exists. Recent progress has been made. In 2013, unsolved, Yitong Zhang proved that infinitely many prime pairs exist with gaps less than 70 million. Collaborative efforts have reduced this bound dramatically, but the final step to proving gaps of 2 remains elusive. The conjecture illustrates how prime numbers, so central to mathematics and cryptography, still conceal fundamental mysteries. Emergence and complexity. How do simple rules create complex behavior? Cellular automata demonstrate that simple algorithms can generate intricate, seemingly unpredictable patterns, but we cannot predict the outcome without running the simulation. This is emergence, higher-level complexity arising from lower-level simplicity. It appears everywhere from physics to biology to economics, but we have no general theory of emergence. We cannot predict when or how it will occur. As physicist Philip Anderson noted, we cannot explain emergence even in physics, let alone in biology or social systems. Understanding emergence might be crucial for bridging the gap between fundamental physics and the complex world we experience, but it remains a deep, unsolved problem in mathematics, physics, and philosophy. Earth sciences, climate, and geology. The snowball Earth events. Multiple times in Earth's history, the entire planet may have been covered in ice. These snowball Earth events left geological signatures, glacial deposits in tropical regions, strange carbon isotope ratios, and iron formations that suggest ice-covered oceans. But how did Earth enter these frozen states? And more mysteriously, how did it escape? With ice reflecting sunlight, the planet should remain frozen indefinitely. The leading explanation involves carbon dioxide buildup from volcanic eruptions. With ice covering the oceans, CO2 couldn't be absorbed, building up over millions of years until greenhouse warming melted the ice. But the details remain unclear. What triggered glaciation? How complete was the ice coverage? Did some regions remain ice-free, preserving life? And how did life survive these catastrophes? These events profoundly shaped Earth's evolution and may have driven major biological innovations. But much about them remains speculative. The extinction of the dinosaurs. An asteroid impact 66 million years ago caused a mass extinction that ended the dinosaurs' reign. Evidence is clear. A massive crater in Mexico, shocked minerals, a worldwide layer of asteroid debris. But the impact alone may not explain everything. The extinction was selective. Some groups vanished while others survived. Mammals, birds, crocodiles, and many marine organisms persisted. And volcanic eruptions in India's Deccan Traps occurred simultaneously. Massive lava flows released enormous quantities of gases. Did volcanism stress ecosystems, making them vulnerable to the asteroid's final blow? The exact mechanisms of extinction remain debated. Did darkness from dust clouds kill photosynthesizers? Did acid rain poison ecosystems? How long did recovery take? We know the broad story, but not all the details of this pivotal event in Earth's history. The Earth's magnetic field reversals. Earth's magnetic field flips periodically. North and south magnetic poles swap positions. The last reversal occurred 780,000 years ago, but they happen irregularly every few 100,000 years. What causes reversals? The field is generated by flowing liquid iron in Earth's outer core. Computer models can simulate the process, but we don't fully understand the trigger or timing. Are we due for a reversal? Some measurements suggest the field is weakening, possibly indicating an approaching flip. But the field has weakened before without reversing. During a reversal, the field becomes chaotic and weak. Does this threaten life? Would cosmic rays increase? Would satellites fail? These questions matter, but without witnessing a reversal, we're uncertain about its effects. The core mantle boundary. Deep beneath your feet, roughly 2,900 kilometers down, lies one of Earth's most mysterious regions. The core mantle boundary separates the liquid iron core from the solid silicate mantle. Recent research reported in 2024 discovered what appears to be ancient ocean floor pooled at this boundary, stalled in its descent. This finding challenges our understanding of plate tectonics and Earth's internal structure. Seismic waves reveal complex features, ultra-low velocity zones, partial melting, chemical reactions between core and mantle. But interpreting these signals is difficult. What is the boundary's composition? How does heat transfer from core to mantle? Do chemical reactions occur at this interface? These questions affect our understanding of volcanoes, magnetic field generation, and Earth's thermal evolution. Earthquake prediction. We can identify earthquake-prone regions and estimate probabilities over decades. But predicting specific earthquakes days or hours in advance remains impossible. Earthquakes result from stress buildup and sudden release along faults. But the exact moment of failure depends on complex factors we cannot measure. Small perturbations can trigger or delay rupture unpredictably. Some precursory signals have been proposed: changes in groundwater levels, electromagnetic emissions, animal behavior. But none have proven reliable. False alarms and missed events plague prediction attempts. Is earthquake prediction fundamentally impossible due to chaos in the system? Or will better monitoring and understanding eventually permit forecasts? The answer affects millions living in seismically active regions. The origin of Earth's water. Earth is a water world, but where did the water come from? The inner solar system was too hot during planet formation for water to condense. So how did Earth acquire its oceans? One hypothesis proposes comets, icy bodies from the outer solar system, delivered water through impacts. But analysis of comet water shows different isotope ratios than Earth's oceans. Asteroids are a better match. Certain types contain hydrated minerals that could have supplied water. But did they deliver enough? And when did Earth's oceans form? Recent evidence suggests some water may have been incorporated during Earth's initial accretion. But the full story of how our planet became wet remains uncertain. The magnitude and duration of past climate changes. Earth's climate has varied dramatically over geological time. Ice ages alternate with hothouse periods. Carbon dioxide levels have fluctuated wildly. But reconstructing ancient climates is challenging. We use proxies, ice cores, sediment layers, fossil distributions, isotope ratios. Each method has limitations and uncertainties. Past climate changes may have been faster or more extreme than our reconstructions suggest. Understanding past climate helps predict future changes, but gaps in the record and uncertainties in proxies mean we don't have complete knowledge of Earth's climate history. How quickly can climate shift? What are tipping points beyond which change becomes irreversible? These questions matter urgently as modern climate changes, but the geological record provides only partial answers. Deep Earth's composition. We've directly sampled only the uppermost crust. Everything deeper comes from indirect measurements: seismic waves, magnetic fields, volcanic emissions, meteorites assumed to represent planetary material. What is the lower mantle made of? Does the core contain elements besides iron and nickel? Are there reservoirs of carbon, water, or other volatiles hidden deep within Earth? Recent discoveries keep surprising us. A possible ocean's worth of water, locked in minerals hundreds of kilometers down. Ultra-low velocity zones hinting at partial melting. Seismic anomalies that challenge our models. Earth's interior remains largely unexplored, a vast unknown realm beneath our feet. Submarine freshwater reservoirs. In 2024, scientists discovered vast freshwater aquifers beneath the ocean floor, containing potentially drinkable water in porous sediments. How did freshwater accumulate underwater? How extensive are these reservoirs? How do they connect to land-based aquifers? Can we access them without causing environmental damage? These discoveries challenge our understanding of Earth's water cycle and raise tantalizing possibilities for water resources. But many unknowns remain. The formation of Earth's moon. The leading theory proposes a Mars-sized object struck Earth early in its history. The debris coalesced into the moon. This giant impact hypothesis explains many features: the moon's composition, its orbit, Earth's tilt. But recent simulations suggest problems. The impact might have left Earth and moon with different compositions, contrary to observations. Alternative scenarios, including multiple smaller impacts or capture of a formed body, have been proposed. The moon's origin affects our understanding of Earth's early history and the solar system's violent youth. But despite decades of study, uncertainties remain. Medicine, health, and the human body. The placebo effect. Give someone a sugar pill and tell them it's medicine. A surprising percentage will improve. This is the placebo effect, and it's remarkably powerful. Placebos can reduce pain, alter brain chemistry, affect immune function, and influence a wide range of conditions. Imaging studies show real neurological changes when people take placebos. The effect is not imaginary. It's a genuine biological response. But how does belief trigger physical changes? What mechanisms allow expectation to modify symptoms? The interplay between psychology and biology remains poorly understood. Recent research shows placebos can work even when people know they're taking placebos, suggesting the ritual of treatment matters beyond deception. But this deepens rather than resolves the mystery. Anesthesia's mechanism. We've used anesthesia for over 170 years. It works reliably, allowing pain-free surgery. But we still don't fully understand how anesthetic drugs eliminate consciousness. Different anesthetics have different molecular structures and targets. Some affect neurotransmitter receptors. Others alter membrane properties. but the final common pathway to unconsciousness remains unclear. Why does consciousness disappear? What brain states does anesthesia create? How is anesthetic unconsciousness different from sleep or coma? Recent research suggests anesthetics may disrupt the brain's ability to integrate information, breaking apart the unified conscious experience. But this is a correlation, not yet a complete explanation. That we can reliably eliminate consciousness without understanding the mechanism highlights how little we know about awareness itself. Autoimmune diseases. The immune system protects us from pathogens, but sometimes it attacks healthy tissue, causing autoimmune diseases. Rheumatoid arthritis, lupus, multiple sclerosis, and over 80 other conditions. Why does this happen? Genetic factors play a role, but identical twins don't always share autoimmune conditions. Environmental triggers have been proposed: infections, toxins, stress. But specific causes remain elusive. What breaks immune tolerance? How do immune cells that should recognize self as non-threatening become activated? Can we predict who will develop autoimmune diseases? Treatment often involves suppressing the immune system broadly, which increases infection risk. We need better understanding to develop targeted therapies. The mechanism of general aging. Why do we age? Cells accumulate damage, DNA mutations, protein misfolding, mitochondrial dysfunction, telomeres shorten, inflammation increases. But which of these causes aging, and which are just correlations? Some organisms don't seem to age. Certain jellyfish can revert to earlier life stages. Hydra may be biologically immortal. What do they do differently? Theories of aging abound. The disposable soma theory proposes aging results from trade-offs between reproduction and repair. The free radical theory suggests reactive oxygen species cause cumulative damage. But no single theory explains all aspects of aging. Recent research targeting specific pathways has extended lifespan in laboratory animals. But translating this to humans remains challenging, and we still don't fully understand why multicellular organisms are programmed to deteriorate. Migraine causes. Migraines are severe, debilitating headaches affecting millions. We know cortical spreading depression, a wave of neural activity, is involved. We've identified genetic factors and triggers, but the fundamental cause remains mysterious. Why do some people get migraines while others don't? What initiates an attack? Why do migraines often stop after pregnancy? Recent treatments targeting CGRP, a signaling molecule, help many patients. But they don't work for everyone, and their success doesn't fully explain migraine mechanisms. The complex interplay of vascular changes, neural dysfunction, and genetic susceptibility continues to challenge researchers. Long COVID. Following acute COVID-19 infection, some people develop persistent symptoms: fatigue, cognitive dysfunction, breathing difficulties. This is long COVID, and it's poorly understood. As noted in research from 2025, potential mechanisms include viral reservoirs, immune dysregulation, microclots, microbiome changes, and mitochondrial dysfunction. Different patients may have different underlying causes, but we lack definitive biomarkers or universal treatments. The NIH Recover program is investigating, but answers remain elusive. Long COVID illustrates how viral infections can trigger complex, persistent conditions we don't fully understand. Similar post-infection syndromes have been recognized for decades, but remain mysterious. Alzheimer's disease. Alzheimer's destroys memory and cognition, affecting millions. Brains of patients show distinctive features: amyloid plaques, tau tangles, neuron loss. For years, the amyloid hypothesis dominated. Plaques cause disease. But drugs that successfully clear amyloid often don't improve cognition significantly. This suggests the relationship between plaques and symptoms is more complex than thought. Are plaques a cause or consequence? Are tau tangles more important? Does neuroinflammation drive progression? Recent research explores multiple mechanisms, but we still lack a complete understanding. Without knowing the fundamental cause, developing effective treatments remains challenging. Alzheimer's represents one of medicine's most pressing unsolved problems. The effectiveness of psychotherapy. Psychotherapy helps many people with mental health conditions, but we don't fully understand why it works or what mechanisms produce benefit. Different approaches, talk therapy, cognitive behavioral therapy, psychodynamic therapy, seem equally effective for many conditions. This suggests common factors, rather than specific techniques, may matter most. But what are those factors? The therapeutic relationship? The act of structured reflection? Behavioral changes? Neuroplastic changes in the brain? We can measure outcomes, but the causal pathways from talking to psychological improvement remain incompletely mapped. The origin of autoimmune diseases. Despite affecting millions and involving over 80 distinct conditions, we don't fully understand what triggers autoimmune responses. Genetics clearly matter, but environmental factors are crucial. The hygiene hypothesis proposes that reduced childhood exposure to microorganisms increases autoimmune risk. But this doesn't explain why autoimmune diseases are increasing even as we understand more about hygiene. Could gut microbiome changes play a role? Viral infections that trigger misdirected immune responses? Chronic low-level inflammation from modern diets? The interactions between genetics, immunity, microbiome, and environment are complex, and we're far from a complete picture. Prion diseases. Prions are misfolded proteins that cause other proteins to misfold, creating a cascading reaction. They cause invariably fatal neurodegenerative diseases: Creutzfeldt-Jakob disease, mad cow disease, Kuru. How can a protein be infectious? How does misfolding propagate? And why are prion diseases so resistant to normal sterilization methods that destroy bacteria and viruses? We know prions spread the misfolding pattern like a template, but the detailed mechanism and why some proteins are susceptible while others aren't remain mysterious. Can other diseases involve prion-like mechanisms? Evidence suggests Alzheimer's and Parkinson's may involve similar protein misfolding cascades, though not true infectiousness. Strange phenomena and unexplained events. Ball lightning. Witnesses describe glowing spheres floating through the air during thunderstorms. They pass through walls, roll along the ground, and disappear with a pop or fade away silently. This is ball lightning, and it defies explanation. Despite thousands of reports, ball lightning remains poorly understood. Its rarity makes study difficult. No one has successfully created ball lightning in a laboratory that matches eyewitness descriptions. Proposed mechanisms range from plasma vortexes to chemical reactions in aerosols to microwave interference patterns. But none fully explain the observed properties: how ball lightning persists for seconds to minutes, passes through solid objects, or occasionally causes damage. The phenomenon sits at the boundary between verified physics and anecdote. Real enough that serious scientists investigate it, mysterious enough that we still don't know what it is. The bloop. In 1997, underwater microphones detected an extremely loud, ultra-low frequency sound in the Pacific Ocean. Dubbed the bloop, it was loud enough to be heard across thousands of kilometers. Its frequency pattern suggested a biological source, but it was far louder than any known animal. Blue whales, the loudest animals, produced sounds many times quieter. Later analysis suggested the sound might have come from ice quakes, fracturing of massive icebergs. But the interpretation remains debated, and the true source was never definitively identified. The bloop represents a class of unexplained sounds detected in the ocean, reminding us how little we know about the deep sea. The wow signal. On August 15, 1977, a radio telescope detected a powerful, narrowband radio signal from space. It lasted 72 seconds, matching expectations for an artificial extraterrestrial transmission. The astronomer who found it wrote, "Wow," in the margin of the printout. The signal has never repeated, despite numerous attempts to detect it again. Its source remains unknown. Was it aliens? A natural but rare astronomical phenomenon? A terrestrial signal that somehow appeared to come from space? Without repetition, we cannot study it further. The wow signal remains one of the most intriguing unexplained detections in the search for extraterrestrial intelligence. Fast radio bursts. Astronomers detected the first fast radio burst in 2007, though it was actually recorded in 2001. These are millisecond-long bursts of radio emission from distant galaxies, releasing as much energy as the sun produces in days. What causes them? Magnetars, highly magnetized neutron stars, are one leading candidate. Colliding neutron stars, or black holes, are another. But FRBs show diverse properties, suggesting multiple origins. Some repeat, others don't. Some show complex frequency structures, others are simple. Each discovery reveals new varieties, expanding rather than constraining the mystery. We've detected thousands now, but fundamental questions remain unanswered. The Tunguska Event. In 1908, an explosion flattened 2,000 square kilometers of Siberian forest. The blast, equivalent to 10 to 15 megatons of TNT, was heard hundreds of kilometers away. But no crater was found. The most accepted explanation is an asteroid or comet that exploded in the atmosphere before reaching the ground. But exactly what it was and why it exploded remain uncertain. Some evidence suggests it might have been an unusually weak, porous asteroid that fragmented completely. Others propose a comet's icy nucleus. Without fragments to analyze, we're left with indirect evidence. The event demonstrates that even recent, well-witnessed phenomena can remain partly mysterious. The Pioneer Anomaly. NASA's Pioneer 10 and 11 spacecraft, launched in the 1970s, exhibited an unexplained deceleration as they traveled through the outer solar system. They were slowing down more than expected. Was this new physics? A modification of gravity at vast distances? Or something mundane? After years of analysis, researchers concluded the anomaly came from thermal radiation. Heat from the spacecraft's power source, creating a tiny but persistent push. Mystery solved, but the process illustrated how difficult it is to account for all factors in precision measurements. The Bermuda Triangle. More ships and aircraft have supposedly vanished in the western North Atlantic than in comparable regions elsewhere. This is the Bermuda Triangle legend. But is it true? Statistical analyses suggest disappearance rates in the Bermuda Triangle don't exceed those in other heavily traveled oceanic areas. Many supposed mysteries have mundane explanations, yet the legend persists. Why are we drawn to mysterious disappearances? The Bermuda Triangle tells us more about human psychology and our love of mystery than about anomalous phenomena. Sonoluminescence. Hit water with sound waves, and bubbles form. Under the right conditions, as these bubbles collapse, they emit brief flashes of light. This is sonoluminescence, discovered in 1934. How does sound create light? The collapsing bubbles reach enormous temperatures and pressures, possibly tens of thousands of degrees. but the exact mechanism of light emission remains debated. Theories range from thermal radiation to electrical discharges to exotic quantum effects. Some even proposed fusion reactions occur in the bubbles, though this remains speculative. Sonoluminescence demonstrates that even benchtop phenomena can harbor deep mysteries. Cosmic rays, above the GZK cutoff. Cosmic rays are high-energy particles from space. Theory predicts they shouldn't exceed certain energies due to interactions with the cosmic microwave background radiation. This is the Greisen-Zatsepin-Kuzmin GZK cutoff. But we've detected cosmic rays with energies above the cutoff. Where do they come from? What accelerates them to such energies? Possibilities include supermassive black holes, gamma-ray bursts, or exotic phenomena we haven't imagined. Each ultra-high energy cosmic ray detection is a puzzle pointing toward astrophysics we don't understand. The Fermi bubbles. Giant gamma-ray emitting structures extend above and below the Milky Way's center, discovered in 2010. These Fermi bubbles span 50,000 light-years, but are invisible to optical telescopes. What created them? Past activity in the galactic center's supermassive black hole? A burst of star formation? The structures are millions of years old, but their origin remains uncertain. They suggest the Milky Way's recent past was more violent than we thought, but the specific events that created these enormous features remain mysterious. The closing, the pattern we cannot see. And so we reach the end of our journey through mystery. 100 questions that science, for all its brilliance, cannot yet answer. 100 edges where knowledge meets the unknown. But before you drift off to sleep, I want to share something that might keep you awake just a little longer. Something that changes the meaning of everything we've explored tonight. Look at what we've discovered. Dark matter and dark energy, making up 95% of the universe. Invisible, unmeasurable, except by inference. Quantum particles that exist in superposition until observed. Consciousness that arises from neurons, but might be fundamental to reality itself. Life that began through processes we cannot recreate. Time that flows in only one direction for reasons we cannot explain. Do you notice the pattern? Every mystery we've explored tonight has something in common. They all involve aspects of reality that resist direct observation. Things that exist only through their effects. Phenomena that change when we try to measure them. Processes that worked once but never again. Questions that deepen rather than resolve as we study them more closely. What if, and stay with me here, what if the reason science can't explain these things isn't because we lack the right tools or theories? What if some aspects of reality are fundamentally unknowable? Not by accident, but by design. Not because we're not smart enough, but because the universe itself maintains secrets. Physicist John Wheeler once proposed a radical idea, that the universe might be participatory, that the act of observation plays a role in creating reality. The quantum measurement problem seems to support this. The observer effect in particle physics demonstrates it. And consciousness, that strangest mystery of all, might be the mechanism through which reality observes itself. If Wheeler was right, then these mysteries aren't bugs in our understanding. They're features of reality itself. The universe doesn't just have secrets, it requires them. And the boundary between what we know and what we cannot know might not be arbitrary, but fundamental. Here's the final twist. The thought I'll leave you with as you drift towards sleep. Remember those anomalies in the cosmic microwave background I mentioned at the start? The patterns that shouldn't be there? Some cosmologists have proposed something extraordinary. They suggest these anomalies might be evidence of our universe colliding with another universe during the Big Bang. If true, it would mean we live not in the universe, but in a universe, one bubble in an infinite foam of realities, most of which we cannot see, cannot reach, and cannot prove exist. And if that's true, then every mystery we've explored tonight might have an even deeper answer lying in those other universes. Dark matter might be matter from those other realities, bleeding through. Dark energy might be the pressure of those universes pushing against ours. Consciousness might extend across realities in ways we cannot measure. Or perhaps none of that is true. Perhaps these mysteries have mundane explanations we'll discover tomorrow, or in a decade, or in a century. Perhaps our descendants will look back and smile at how primitive our understanding was, the way we smile at medieval astronomers who thought the stars were fixed to crystal spheres. But I suspect some mysteries will endure. Not because they're impossible to solve, but because they're impossible to completely solve. Because reality might be fundamentally, beautifully, necessarily mysterious. The Japanese concept of mono, no aware, speaks of the poignant awareness of impermanence, the beauty of transient things. Perhaps knowledge too is transient, always incomplete, always changing. What we know today will be refined tomorrow. What seems certain now will prove approximate later. And the mysteries we cannot solve might yield to tools and ideas we haven't imagined. Or they might remain, eternal and beautiful, the universe's way of reminding us that wonder is not ignorance, but wisdom's humble beginning. Sleep well tonight, knowing that you live in a universe stranger and more beautiful than any story we could tell. Dark matter threads through your body this very moment. Your consciousness arises from processes we cannot explain. You began from chemistry we cannot recreate. And somewhere in the vast silence, in the 95% of the universe we cannot see, mysteries wait, patient, eternal, calling. If these gentle explorations through the unknown brought you peace, curiosity, or simply a restful companion for sleep, consider subscribing to Sleepable Science. It helps others find their way here too, one curious dreamer at a time. Thank you for listening, and may your questions be as beautiful as the answers you seek. Sweet dreams. And remember, in the darkness between what we know and what we don't know, that's where the really interesting stuff happens.